So I like these problems. I had a professor that I taught with back at West Point in 1997, I think, and he told me just because I like it doesn't mean it's important. So this is one of them. I like it. It's not really that important. Um, so the reason that you're getting this problem is to understand what these symbols mean. We use a lot of notation in math, and it's because it used to be very difficult to typeset. And so if I wrote this out in words, it would be difficult to type. In fact, my professors at Georgia Tech, their papers were typed by secretaries. And so it would be an enormous job to type these things out in words. And so we use this shorthand. So peeling out what this shorthand means, let's look at A. This little hash mark here is not a -2. What it is, it's the limit of f of x as x approaches 2 from the left. Decoding that further, what that really means is it's the answer to the question, what's y getting close to as x gets close to 2 from the left? So I'm approaching 2 from the left on the graph, and y is getting close to 3. So the answer to this is 3. So it's really a decoding of all these symbols. Let's go to the next one. At the next one, it's the answer to the question of what is y getting close to as x goes to 2 from the right? And you can see here it's going to 1. Notice that there's a hole right there at 2. That means that f of 2 is not equal to 1. It's just that the y values are all getting closer to 1. At x equals 2 itself, the colored in point is y equals 3. So the value at f of 2 is 3. Why is this important? Well, I didn't look at the next problem, but I first noticed that these two things are not equal. And if they're not equal, that's one of the checklists that I'm going to give you in class that says that the limit doesn't exist. So for the limit to exist, the left side and the right side must be equal. And so they're not equal, so the limit itself doesn't exist. I just said that at x equals 2, it's colored in at 3. And so that's the value at x equals 2 is 3. If this all seems weird, these are kind of concocted examples that mathematicians spend a lot of time on. I actually brought it into an applied class once, and I said, oh, Dr. Loss, you haven't thought about these things. And he said, the examples you're giving me are stupid. They don't show up in applied problems. And I never forgot that, because there's the practical side and there's the mathematician side of I've got to be exactly right and precise in what I'm saying. The fourth, the E problem, what is here the left side and the right side, they didn't split it up into two pieces, but as I approach x from the left and the right, the y value is approaching 4. So the limit exists, and it's 4. But there's no colored in point at 4. It's just got a hole. So f at 4 doesn't have a value. It doesn't have a y value. So f at 4 does not exist. This is a totally cooked up problem. It does, I guess, sometimes appear in some application, but it doesn't show up much. And so these are just I guess, lifts to get used to weird things. So that's number 4. It's very similar to number 5. Text me if you have enough problems. I'm not sure that I gave enough explanation for this.